Hello, Stardust Explorers. Welcome back to this channel. And my name is Adeze Ipik, aka Astro Princess. If this is your first time, you're welcome. Here we help people to understand how to solve physics certificate examinations, both from explanation standpoint and also just making sure you know how to get what the examiner expects of you. So this is a place for you if you're interested in any of this. Also, we shed light into different activities, events, and objects and phenomena in our universe, and try to understand why they happen the way they do. Mostly shedding light on some of the events around us, just trying to understand the universe, understanding our environment a bit more. So if you have any science-related questions, especially if you are worried about why some things are happening, especially if you care about the scientific explanation, then this is the channel for you. And we do a lot of other things as well, educational consulting, if you want career-related coaching and advice. Yeah, these are all part of the contents we share on this channel. So yeah, feel free to share, subscribe, and stay tuned. Okay, so today we are continuing with solving one of the years from the WASSCE, which is the West African Certificate School Examination past question. We have all started this thing until we are now in the second part of the theory question. So if you care about the previous videos, go back to our channel where we see all the other questions that have been answered. So on today's episode, we'll be considering the question that involves thermal conductivity. So here is the question, and I will read. Define coefficients of thermal conductivity of a material. 2, the diagram below, as a diagram as you can see, illustrates a composite bar of iron and copper. So this is a bar that has two different parts. One is made of iron, one is made of copper. The bar is insulated along its sides, and it has a diameter of 10 millimeter. The length and the thermal conductivity of the iron are 0.15 meter and 40 watts per meter per Kelvin, respectively. And those of copper are 0.05 meter and 360 watts per meter per Kelvin, respectively. So you are given parameters for iron and parameters for copper. If the free ends of the iron are copper and copper are kept at 100 degrees Celsius and 0 degrees Celsius for the two of them, calculate the temperature at the interface between the bars. Also rate of heat flow along the bar. Sounds like a lot of questions, a lot of information, but you take it one step at a time, one sentence at a time. All right, so beginning with the first one, define the coefficients of the thermal conductivity. So just to give us more context, I had to pull up this image from one of the sites. It will be on the link in the description if you want to go and read in details. But the coefficient of thermal conductivity of any material is the rate at which heat flows. So heat energy actually flows, and the rate at which that happens through a material per unit area, per unit thickness, and per unit temperature gradient is what we call the coefficient of the thermal conductivity of that material. So this differs for different materials, right? And in a simple way, it's a measure of how well a material conducts heat. So we have this diagram trying to explain what we mean. So if you have a box, for example, of thickness given the area of this box because it's rectangular. So the shape of the material matters. So in this case, this is a rectangular shape. Then the area will be length times breadth. So the area is also given. So if you apply heat energy, as you can see here, if you apply heat energy at the beginning, there is a temperature usually at the beginning also. Let's call it temperature 1. Now, there is a thickness, remember, so this heat will have to flow from one end to the other. So there is a flow of heat, right? And there is a new temperature as a result, which is T2. Now, this material has what is unique to itself, known as the coefficient of thermal conductivity. So if it is one material, then that material has the coefficient of thermal conductivity, and because of the heat flow, the temperature has now changed from what it used to be before you applied heat to a new temperature after you applied heat. So you can estimate the temperature difference or change in temperature by subtracting the two. Now, the rate of which that heat energy flow from the beginning to the end is what we call the thermal conductivity rate. So again, this is just to help you visualize what you are asked here. And for this question is a definition question, so you need to make sure you get the first part of it, which is the important part, right? The rate at which heat flows through a material per unit area, per unit thickness, and per unit temperature gradient. What I normally do, this is a way to maybe cheat the assignment. If you know the equation or the formula for that, it's usually easier to get the definition, because the definitions are always related to the formula. If you don't remember the formula, do you remember the units? So if you know the SI unit, that tells you the quantities involved, and that tells you how the definition should be. So that's another bonus that I'm sharing with you. So, which is why it's good to memorize the units, understand the equation. Sometimes when I understand the equation, I don't need to memorize units, because the units come from the equations too, right? The right coefficient that the unit should have, you only know that when you understand the equation. So it's easier to know the equation and save yourself the stress. Once you remember the equation, you derive the units from the equation. So that's a simple way, again, to define anything that has an equation anyway. All right, so I hope that was clear. We'll move on to the next one. Right, so the rate of heat transfer or heat flow, whatever you want to call it, and I'm designating that with Q. Now I'm giving the formula, not the exact thing we just defined, but you will see that what we just defined is K in this equation. So the rate of heat flow, Q, is equals to negative of this coefficient of thermal conductivity called K in this equation, times the area, that's cross-sectional area we talked about in the previous diagram, times the change of temperature, divided by the thickness or the length of the bar, whatever that means in the particular context, okay? So when you remember this equation, it will help you with even getting your first question right. But I want to take us back to the equation, because we need to remind ourselves. So that second question is now referring to this diagram. Now the diagram has two materials, iron and copper, and we are given the parameters for each. They said both sides have the same diameter, 10 millimeters. and the length and their thermal conductivity are also given for each of them. And then we are asked to calculate the temperature at the interface, given that the iron is kept at 100 degrees Celsius and the copper is kept at 0 degrees Celsius. So now keep this image in mind and then look at it here again. I have to bring it up here so that it will help with getting into the solution for that one. So one easy thing I prefer to do is to write down all the given parameters. So first, establish the equation that connects the parameters given to you. When you check that, you will see that this equation of rate of heat transfer is the real deal. So write that down, then begin to list out the parameters. I just think it's easier for your clarity sake to write them out, even though it's already in the equation. So write them down, especially with definition. So for example, I have now given more context to this diagram. I don't know if the one you get for the examination will be to scale anyway, but this one is to scale. What do I mean by being to scale? So when you look at the parameters given, the length or the thickness for iron is small compared to that of copper. So I have put down this diagram to reflect that. And then the one end for the copper is 0 degrees and the other end for iron is 100 degrees. So I've also indicated that just for clarity. So for the side of the iron, I'm listing out the parameters for iron, also for clarity's sake. So you can see that the the coefficient of the thermal conductivity is 40 for iron. The thickness is 0.15 for iron. Then we are given D. Here, D is the diameter. Now, one thing that is important for this question is to understand the shape of the material, because you need to calculate the area. So the shape of the material will determine the formula to use for calculating the area. Now, in this question, I didn't see a clear statement saying that the bar is a circular bar. The bar could be a rectangular bar, it could be a circular bar, it could be any form of shape somehow. But I will say that, again, looking at the parameters given to you, you can decipher the likely shape, So here they mention diameter, and straight up, you know that only circles have diameters. So that tells me that the bar is a circular bar. So the area that I'll be using here will be the area of a circle. Okay, I hope that makes sense. So with that, you can come up with the equation, which is pi r squared. Here I'm using the diameter, that's why it's this way, because the diameter divided by 2 will give you the radius, which is the r in the equation. So this gives you the area of that part for the iron. Okay, so we also have the change in temperature given as there's a value given, which is that one end of iron is at 100, and the middle part, wherever the two of them meet, there is a temperature there called theta. It's part of what we'll be finding. However, for the change of temperature to be accounted for, you have to find what is the right change with respect to iron. So just by drawing this diagram, it makes it easier for you to come up with the right thing. So with this iron, you know that for 100 to be the highest temperature here, then you have that your change in temperature would be 100 degrees Celsius to minus theta. So theta cannot be more than 100. Just with normal reasoning, you can come up with that. Theta cannot be more than 100. So if you have something very hot, you have something again very cold. If you join them together, there will be heat transfer. Now, this heat transfer will continue to go on until they assume an equal temperature called theta. Now, there is no way that temperature will be more than the highest temperature you started off with. It's not possible. So just with that common understanding of the concept, you will be able to get the right framing for the change in theta, so that you don't say theta minus 100. That could mess the whole thing up. So yeah, so we have 100 minus theta in this case, which is the right thing. All right. Now for copper, you also write out everything given to you. In this case, you have the theta, the coefficient of thermal conductivity, the thickness, the diameter, and also the change in temperature. So for the copper, you will see that the extreme temperature for copper is 0 degree, but in between we have this theta. Again, theta cannot be colder than 0 degree. It can't be less than 0 degree. So it has to be because most time for this type of temperature change, they always have to be from the highest to the lowest minus the lowest. You cannot do small temperature minus high temperature. It has to be high temperature minus low temperature. So with that common understanding, you will be able to come up that for copper, the change in temperature would be theta minus 0. I'm taking time to get into these nitty-gritties because this is where it can get messy. So I hope you are following and that you understand what we are doing and why these things are happening the way they are happening. Before I forgot, I was going to mention that the diameter is in millimeter. Remember, when you are solving anything at all, you need to make sure that all your units are in the SI unit. So millimeter is not SI unit. So you need to first convert that. If you notice here, I did that conversion for the two sides. So that gives you 0.01. So you convert with the right equation to make sure you remember the right conversion factor. So for you to move from millimeter to meter, you divide by 1000, and that's what we did. Okay, so I will take it that this is clear, and then we move forward. We are still trying to solve this equation. Okay, so let's get back to the equation again, just to refresh our memories, because what we've just done now is just writing down parameters, just making it easy for us to solve and understand, but we have not answered the question yet. So calculate the temperature theta at the interface between the bars. That's the question. At the interface between the bars. Okay, now one thing you have to note, by the way, I am now realizing that I think I switched things up. So instead of giving iron a much longer thickness, I gave it to copper. But that's by the way, you can adjust that. So getting back to the equation, we have to think about what happens when you bring two materials of different temperatures and there is heat exchange. I said it briefly now that the heat will continue to exchange until an even temperature is attained. Now, what happens at that point also is that the heat energy of the other material is now equal to the heat energy of the other. So the two materials will be sharing the same heat energy at that point. Now, with that understanding, you can equate the rate of heat flow of the two materials. And that is what we are doing here. That will lead us to solving that first question. So I have given the formula in the previous slide for the heat flow, or the rate of heat flow. There is a negative sign there, which is the fact that there is heat transfer. Sometimes it doesn't really affect your result, but it's just good practice to keep it. So if you now substitute your values for that of iron and that of copper, this is what you get. You can go back and just look at what the area is for each one, substitute them into that equation for Q, substitute the theta, the change in theta, the L, which is your thickness, for each of them. You will get this. Now you have to be careful with solving equations like this. Do not rush it, and take your time one after the other. But one thing that is clear here is that some things can cancel out. All right, that makes your work a little less messy. So when you take them out, you can of course get down to this equation down here, and from there you can get here. Now from this point you can now do what we call the cross multiplication. When you cross multiply, you get what we have here. Then of course take all of the ones that have theta together and the other ones without theta together. When you do that properly, rearranging them will give you theta to be 3.5714 degrees Celsius. So this will be the even temperature, the equal temperature that the two materials would attain. I hope that makes sense. All right. If you were asked to correct to significant figures or decimal places or whatsoever, make sure you give the first solution result, which is usually preferred to be in 4 or 3 decimal places. 4 or 3 decimal places is the standard. Sometimes they can be specific, but it's better to get up to 4 or 3 decimal places. Then if you were instructed to round it off, you can then round it off. Even without being told, you can round off maybe to 1 decimal or 2 decimal places, but make sure you still have your original answer before the next level of the answer, which is where you now rounded it up. Okay, because sometimes there will be separate marks for each one, whether it's rounded off or the original one. Sometimes they have separate marks. But if you round it up and then you did not give the original one and you were not asked to round up, you could miss a mark just for that. So giving out your original result is very important. And the steps, you must show all your workings, show all your steps for you to get full marks. Just establishing that the heat of iron is equal to that of copper gives you 1 mark. That's different from the formula. And then being able to substitute properly gives you another mark. Then solving all the way until you get to the right answer with the right significant figures and decimal places expected and the right unit. Do not forget that the unit is also very important. You miss half a mark for any units you miss. So do not neglect any little details here. Okay, I hope that was clear. Let's quickly finish up this question. Okay, so that question is asking for the rate of heat flow. What is Q? Remember, we just solved for theta. So now we have theta, we can solve for Q because that's the only unknown we have all the while. So which means you can choose from any of the equation for either copper or iron, and that could be used, and because they should give you the same result, Okay, so when you use any of them, substitute the value of theta, and then in any one you prefer to choose, solve it carefully. Then that should give you the same value of 2.0196 watts. Now, it's either you leave it in watts or you leave it in joule per second. The two of them are allowed SI units. Okay, and that should be the answer to this question. I don't know if you have any question, feel free to ask. But what I would advise is that you have a good understanding of the concept, because it helps with even the solutions that follows, like what we just did. And as you can see, right, from the coefficient of thermal conductivity, copper has a much higher thermal conductivity than iron. I mentioned in the last video why this is so, because copper is a better conductor. It moves. It also allows electricity to flow easily, the same way it allows heat. So this is why we use copper for producing cables a lot. There are other reasons too, like copper is good. Now this means that copper is more efficient at conducting heat compared to iron, right? And given this scenario, copper will transfer heat more rapidly than iron will do, because of that higher thermal conductivity. Okay, I hope this was what it, and I hope it gives you clarity if you are struggling with this question in particular. And I will wrap up by reminding you to be patient with yourself and trust the process. There is always a way of escape. So I will see you in our next one. Do not forget to subscribe to our channel at Discovery Stardust. Comment, like, and share this video. And take care, and we'll see you next time. Bye.